All right. So I put up these reduction exercises on your Canvas. I don't know if you had a chance to print them out, but if not, you can just use the document that I'm sharing. What I'd like for you to do is to take a look at this and think about how you would do the first three problems. We'll do the first three, and then we'll switch over to the whiteboard and we'll work them together. So see what you can do with this. Problem number 1, 2, and 3. We're actually going to do the whole sheet, but we'll just do the 1 through 3 first, and then we'll work them on the board. Then we'll come back to this document. So see what you can do with this, and I'll check in with you in just a second.
So just a quick question. Were you basically saying like this is what the fourth exam is going to be like? You're muted right now.
Okay, sorry about that. I always forget to unmute myself. Yeah, so basically, the exam is not just this. This is a part of it. I think really what you want to pay attention to is what we're going to do on Monday. But you need all of the stuff we're doing now to understand what we're going to do on Monday. And I would say that if you understand what we're going to do on Monday, then you're in pretty good shape for exam 4.
Okay, cool. Thank you.
All right. Okay, so if you just logged on, don't forget to send me a text 494-6162, area code 513, and we're working on problems number 1, 2, and 3 right now on this sheet. Okay, so the first problem asks us to find the domain of the expression, and they want a standard SOP, and then they want us to use the truth table to get the POS. So the domain is just the list of variables in each term. There's an A, there's a B, there's a C. So my domain is ABC. So the domain is just a list of the variables in the expression. We want a standard SOP. A standard SOP, we have an SOP now, but it's not standard because in the standard SOP, every member of the domain will be in each term of the expression. And I see right here that that first term is missing a C. So to make this a standard SOP, I need to get a C in there. And the way we're going to do that is we're going to OR that term by the thing that's missing and its complement. So I'm going to take a term, it's missing the C, so I'm going to AND it. I said OR. I mean, I'm going to AND it with C or not C. And I'll expand the expression, and when I do that, I'll get ABC or ABC. I'll take this one into that second variable or complement. I expand this to ABC or ABC not. Then I'll add that to my expression here. So I can get rid of this and add to that what is logically equal to, which is this one right here. So I got A, B, C, or A, B, C, and the C is knotted. And then you know from those rules, those Boolean rules, that if I OR something with itself, it's just the thing that I'm ORing. So right here, I'm ORing ABC and ABC together. It's repeated so I can get rid of one of those. So my actual expression looks like that. I guess I call it Y. We'll call it Y. Okay, so now I've changed the non-standard SOP to a standard SOP. And so now, since it's standard, we can actually write the truth table for it. So we'll get the truth table, and then we'll use that truth table to get the POS. So I got three variables. Remember the number of rows in the truth table is 2 to the nth power, where that n is the number of variables. So we got three variables. 2 to the third is 8. I need a truth table with 8 rows. Start counting with 0. Alternate every other bit here. Every 2 bits here. And every 4 bits here. If you do it that way, you're counting in binary. Now remember that in this standard SOP, the SOP tells us where the ones are in the truth table. So basically, if you go back to what we said in the last class, you can write the binary value of each of these terms, but just if you have a variable, you're gonna write the variable as a 1. If you have a complement, you'll write it as a 0. So this binary value would be a 1, 0, 1, 1, 1, 1, and a 1, 1, 0. So this is mapping 2 rows in the truth table. And so basically, I have a 1 at 101. So at 101, I'll put a 1. I have a 1 at 111, so I'll put a 1 here. And I have a 1 at 110, so I got a 1 there. All these other rows are zeros. So SOPs evaluate to 1s. We were asked to find the POS. Well, POS, that maps to the zeros in the truth table. It indicates where the zeros are. So basically, all of these zeros right here, all of those rows are rows for our POS. They asked us to find the POS. So basically what you'll do is just take and we're going to write our variables OR together. And where I have zeros, I got to not those. So that's one term of my POS, and I would do that for each row. And I not my zeros. And then we were actually concerned about this, which, as I said in the last class, POS is not important for logic control. In digital electronics, you would use it, but for what we're doing, doesn't really do much for us. But basically, you would just take each of these and you would add them together like that. And I won't use time to do that. Does somebody have a message? Does somebody have their hand up? Okay. All right, so that's how you would get a POS from the truth table if you were asked to do that. But again, after the day, I probably will never ask you that again because we're really concerned with these ones right here. Okay, so anybody have any questions over the first three problems? So the idea of this sheet, and I'll give you one more here today, is just to kind of pull together what we've been talking about with the Boolean algebra, the gates, the K-maps, truth tables. We'll pull them together and we can kind of see how this applies to POC stuff. All right, so we did the first three problems. We'll go back to the sheet. And guys, I always forget to remove this. I hope you guys know that if I forget to turn the document off, then you can switch it off yourself. But the bad part about it is when I put this on YouTube, then if I don't remove the document, that stays on the video. So I want to remove that so you can see what my solution to this is. So what we did, we went through, we mapped our ones here from our expression to our truth table. And then it asks for the POS, the product of sums. So you just list out your variables, OR together, and wherever you have something that's a zero, you'll not it. And then you just kind of put it together into an expression and set it equal to some variable. So that's the POS. These are the parts of the POS. And what I was saying was these are really what we're concerned about in logic control, where these ones are. Because that means there's some conditions happening, some condition is happening, and we can program our PLC to respond to those conditions. So that's problem number 1, 2, and 3. If that makes sense to everybody, what I want you to do is the rest of the sheet. And then we'll do one more of these, and then we'll apply some of this to a really, really simple problem before we finish up today. So let's go back to our handout. And now we're going to do 4 through 6. Problems 4 through 6. Okay, so we learned in the last class that this Boolean expression maps to a truth table, and that the truth table maps to a K-map. So that means that this Boolean expression actually maps to a K-map also. So we'll go ahead and use this to put our members in the K-map. This says that we have a member at 101. So 101, we got one right here. We got one at 111. 111 is here. We got one at 110. There's a member right here. And then we'll just figure out what drops out. So if I circle that group right there, I'm moving across the K-map. That means C is out of there. And these are ones, so I don't have any knots there. And then the vertical group, I'm moving this way, so I'm going to keep C. The only thing that drops out is B. A is still a 1, so it's unknotted. So my minimized expression, I end up with my output Y equal to AC or AB. And if you wanted to, since I have that A in both terms, you can factor out an A, and then you'll reduce your instructions in your program by 1. So I can do it either way, it's okay, it doesn't matter. I mean, this is a little bit shorter. So there's our two minimized expressions. You can use the top or the bottom one. Then they want us to show what that looks like using gates. And then in your ladder logic, what would look like using ladder logic. So using gates, I got two AND gates. And the OR. I got input AC and AB. My output is X. If I implement the first one, for this one I kind of like here, I got an OR gate, and I got an and then I got A, C, and B that I'm ORing together. And I guess this should actually be a Y. So there's my program represented using gates. Then they want you to put it in the ladder logic. So if I do this one, or I can do the other. I have B, C, and A, and my output X. So pretty simple, nothing earth-shaking about what we did with this stuff, pretty simple. But again, the idea is not, it's just to kind of pull things together so you can kind of see how they fit together, and then we'll actually use this stuff on Monday. We'll do something light today. We'll do a small exercise today, but the big thing will come on Monday, where we kind of use this to solve a problem that's more practical and that applies more than what you're doing with PLCs. So does anybody have any questions over any of the steps that I went through? I mean, I think it's pretty straightforward. Nothing's difficult, but I want to make sure I'm clear on what I did. Anybody have any questions? Okay, well, I got another one for you. So this time I want you to just go through and do this whole sheet. So you have 6 problems to do. And I'm just going to black out my camera here and my mic, and I want you guys to just do this whole exercise. And then I got it worked out on another slide. I'll show that, and we'll compare your answers to what I got. See what you can do with this, and we'll come back here in about 5 minutes to see what your solution is.
How did you know how many rows were in the truth table?
Yeah, so I'm sorry. Yeah, so the rows, and that's a good question. You'll need that. It's just this equation. The number of rows is 2 to the nth power. That n right there is the number of variables, the number of inputs. So we had 3 inputs, so we needed 8 rows. I think on this problem, but the one we'll do later, we'll just have 2 inputs. So this equation tells you the number of rows. That's the number of variables.
It's just 2 to the n.
2 to the n, right?
Okay.
Okay, let me put that back up there, guys, and go ahead and solve it, and then we'll talk about it. Give you about 2 more minutes and then we'll take a look at the solution. Okay, let's talk about the solution. So problem number one, they want you to write the domain. Clearly the domain is A comma B comma C. But then they tell us to write the expression as a standard SOP. So what's the very first thing you got to do to get the standard SOP? What's step one?
Would be to, sorry, go ahead.
You can go ahead. Oh, well, you have to make sure that all of the terms in the domain are in each product.
Okay. All right. So that's true. So we see that this one right here is missing a B. So we got to add a B to that. What are you going to do with this one, though? Because you're not allowed to have a solid bar. When you're dealing with PLCs, you can't have a solid bar over more than one variable. So how are you going to handle that?
You gotta demorganize it.
You got to demorganize, and that's kind of what I was after. So if you have a bar over more than one variable, you break the line, you change the sign. And if you do that, then you already have a term that has every member in it. So the only thing you're missing here is this one right here. You got to add a B to that. And so you can go through the steps to do that. So I actually kind of worked this out before class. So I'll show you what I have. Okay, so we have a break the line, change the sign, you end up with that. And we'll replace this term with that. And then for this one, you got to add a b to it by expanding this. And then you end up with these terms right here. So check that against what you have to make sure I didn't make a mistake. And I think if you look at that, you'll see it's correct. And then it looks like that we repeated this one, so we got rid of that one. So I ended up with, after everything is said and done, I ended up with this expression, and I went on and I wrote the binary values of each one of these at the bottom so that we can map it to the truth table. So compare that to what you have, and if you have something different, either I'm wrong or you're wrong. But I went over this a couple times, so I think I got it okay. Does that make sense to everybody, the first three? We got 3 variables, so I'm going to need 2 to the third. I'm going to need 8 rows. So here's my truth table. And I just use these binary values down here. They map directly to the rows in the truth table. So this tells me where my ones are in the truth table. It also tells me where my ones are, or my members are in the K-map. So I got the truth table, and then below the truth table, we got the K-map to represent the truth table. So you go through and you minimize, and when I got done, I ended up with this. You guys agree with that solution, or did I make an error?
Looks good.
And then once you minimize, step 5 and 6 at the bottom, then you're good to go. So this stuff right here, I think is, it kind of pulls stuff together, not too difficult. And now what we want to do is use this to actually solve a problem that we can put into your simulator or into a PLC. So I actually got a really, really simple one to start with. I was going to give this to you on Friday, but I figured, well, heck, we might as well go ahead and look at it today. And this is the situation where you have switches in 2 different locations, and you want them to behave a certain way. So look at this design practice 1 exercise, controlling a device from 2 locations. So read the problem statement, and what I want you to do is complete steps 1 through 4, see what you come up with. And then the idea here is that you, in step 3 here, you can use your standard SOP to get a truth table, or you can use a truth table to get the SOP you need to solve a problem. So here we're going to kind of work in reverse. We're going to work off our truth table to give us the SOP that we need to solve this problem. So go ahead and take a read it, do steps 1 through 4, and I'll check in with you in just a couple minutes. This one should be pretty quick. Okay, about 1 more minute and then we'll talk about this, and I think that'll be it for today. So 1 minute. Okay, let's take a look at this. So design and test a PLC program which will allow light to be controlled from 2 locations. If both switches are on or both switches are off, the lamp should be on. For any other position of the switch, the lamp should be off. And they want us to use the addresses below, and they want you to test this in your simulator. So the first thing they had you do is to make a list of all the inputs and outputs along with their addresses. And I want to stress now, I know we've been just kind of working in the simulator, but if you're actually programming a PLC, I mean, you're out in the real world doing a real job, I can't stress enough the importance of step number 1. Now, really depending on what you're doing, often you'll have, depending on what you're trying to automate, you may have just a few inputs. Like, for example, the PLC or the controller in your garage door opener, if you have one, you got just a couple inputs there. You got maybe, you got to know when the door is up, when it's down. You might have some kind of sensor to tell if while the door is traveling down, if there's an animal or a person going through, you want to stop the motor. So you need an input for that. You might have at most, I don't know, maybe 4 inputs, 5 inputs maybe, and an output for a motor. So in some PLC applications, you don't really have a lot to keep track of, but in larger applications, if you're automating a factory or you have some medium-sized application, you really want to list things out and kind of say what's going to connect to what. So you have a list of the addresses. So the right way to do it would be to make a list of all your inputs and outputs and addresses. And then if you actually have to wire this up, then you also can work off that list to make sure that your devices are wired correctly. So that's step 1. So what I did here is I made a list, and I'll show you on the whiteboard in just a second. And then they want to know, well, how many rows are we going to need for our truth table? And we have 2 switches, 2 inputs. 2 to the second is 2, so we need a truth table with, I'm sorry, 2 to the second is 2. 2 to the second is 4, so we'll need a truth table with 4 rows. Now, honestly, this problem, you can get to the solution, of course, without using the truth table. But the point I'm making is to show you that you can use the truth table as a tool to solve a problem, to get a program, or to get the logic to run the PLC. So I'll go to the board here and I'll show you my list. I made a list of inputs and outputs, the addresses, and then it asks for the number of rows. We got to have a truth table with 4 rows. So here's the first couple steps. We'll go ahead and design our truth table. So I just called the switches A and B. So my inputs A and B are my truth table, and my output is a lamp or a light. Call it a light. So I need 4 rows in the truth table. And it says I want the light to light, or or want to output in my program, when both switches are on, that would be this condition, or both switches are off, that would be this condition. It will be false for the other true. So false here and false there. So the terms for my SOP for this, these are both knotted because they're zeros. So I implement that in the PLC. I got A and B, and those are knotted for that row, and I got a repeat of A and B. And that would be my light. So again, the point, this is a pretty simple problem, not rocket science, but you can actually work off the truth table to go backwards to give you the logic that you need to come up with the program or the correct logic for whatever application you're trying to, whatever problem you're trying to solve. So that kind of you just kind of dipping your toe in the pond of the application of what we're going to do with this stuff. And you'll see more of this on Monday when we get together. I'll give you something more kind of akin to what you can expect to see on the final exam. So that's pretty much it for today. Does anybody have any questions over anything we talked about today? Anything that we talked about today, or any questions in general before we sign off?
I have questions on exam 2, which we're looking for part of the program. But yeah, so I'm looking at, I've done the basic programming for exam 2, but number 5 is study the other instructions on the instruction set of your simulator. Add a feature of your own design to the program using one or more instructions that we did not discuss in class. So
Okay,
I mean,
so go ahead.
No, I was just going to ask, is that just kind of find an instruction that we haven't touched on at all and just try to implement it in some way, or?
Yeah.
Okay.
So yeah, so we, if you think about it, if you on your PLC simulator, you have those instructions listed out, and they're kind of grouped together. You have the math instructions, you have all kinds of instructions. You have a lot in your simulation software. So I just want you to kind of explore those other instructions and come up with a feature that you can add to the garage door program to just to make it, put a different spin on it. Really, I'm trying to force you to look at some other instructions. So some handy stuff. There's some logical instructions there that you can play around with. There's some math instructions there that you can learn how to use and play around with. Just go through the instruction set. I'm sure some of you've already discovered that really a lot of the solutions for what we're doing, they're already out there on YouTube. I mean, there's no secret. You can go to YouTube, and even the stuff you've been graded on, you can find a solution on YouTube. However, if you just do that, I don't think you learn much from it. But looking at how to use a new instruction, that's a pretty good tool. So you can, let's say you're going to use some of the math functions, you can go to YouTube and just type in how to use math function in Logic Pro. It'll come up and you'll see some examples. So really all you got to think about is how you would implement that in the program. Maybe you make it, I don't know, count the number of times the door went up or down. So I don't know. I'm leaving that up to you. But basically I want you to just find an instruction that we haven't talked about or used, learn how to use it, in some kind of way implement it into the program. So how you do that, I'll leave that up to you.
All right, sounds good. Thank you.
Anybody else have a question? That was a good question. So guys, I think that's it for today. Now, I'm sure by now you checked Canvas because you had to click on the link to get to this lecture, but I've opened up everything except for the final exam. Everything is out there. We still have plenty of time. Time's still on our side. So exam 2, you already know is out there. I've actually opened up exam 3. You can take a look at least look at it to see what you got to do to finish it so you know how to coordinate your time. So I'd like you to get all that done as soon as you can. That way we can just focus on the final exam. And somebody already asked me earlier today, they said, well, if we can do what we did on the first 2 practice sheets today, does that set us up for the exam? that's a big part of it. But I think Monday is important. If you can do the exercise on Monday, then the exam that we're going to have will be kind of similar to what we're going to do on Monday. So that kind of pulls together everything we've been talking about over the last couple of weeks into one problem, and you have to just kind of show me your skills. And if you understand it, I think you'll be in good shape. But I don't anticipate anybody having any problems with what we're going to do on Monday or the final exam. So I think you'll be pretty pleased. So guys, if you think of something, if you have a question, please text me. Other than that, have a great rest of the day, and I will see you on Friday.
I actually have a quick question.
Sure.
So on the final, is that an accumulative exam over everything, or is it
No.
just?
No, it's just over. Basically, it's over the material that we've talked about since the Lab 5. Now, some of the stuff we talked about logic gates, and we talked about the Boolean algebra. Some of that we talked about before, but that stuff should be second nature. You know, how to use AND OR gates, that kind of stuff. So if you had to study anything, just the last, basically the last couple classes here, this new stuff that we're talking about right now. So it's not over the whole semester, no.
Okay, thank you.
Okay, all right, guys, that's a good question. I'll see you later. And if anything else, just send me a text because I'm on campus all day today until night. So I'll be able to take your texts.